Hello everyone, this is Shivanshu. Welcome to Engineering Hotspot. So, in this lecture series, we are solving the questions that has been asked in the GATE 2023 exam. So now we have solved the solutions of production engineering, questions of production engineering, along with that thermal engineering and uh, industrial engineering. So we have solved question of all these subjects. Now today we will solve the questions of strength of material and machine design. So this is the part one of this lecture, and remaining questions we will solve in the second part. Along with that, you can also purchase the lecture series of production engineering subject from our engineering hotspot channel and app. So at a price of 299 rupees. So go and purchase that. So now let's start this lecture. So this is the question number one that has been asked in the strength of material paper. A cylindrical transmission shaft of length 1.5 meter and diameter 100 mm is made of linear elastic material with a shear modulus of 80 gigapascal while operating at 500 rpm. The angle of twist across its length is found to be 0.5 degree. The power transmitted by shaft at this speed is. So what we have to find out here, we have to find out the power that is given by P is equal to 2 pi n T by 60, right? So this is what we can use to find out the value of the power. So now what we will do, we will try to find out. Here we have given n value, so we need to find out the t value. If we manage to find out the t value, we can have our complete solution. So to find out that, how we can find out? So t will be given by g j theta by l. So what is g j theta by l? So basically g is the modulus of rigidity and j is the polar modulus and theta is the angle of twist and l is the length of the shaft. So we have given here g value, that is 80 into 10 to power 9. Why 10 to power 9? Because we are converting the gigapascal into the Newton per meter square, multiplied by pi by 32 into diameter to power 4. So we have given the diameter value 100 mm. So this will be 0.1 to power 4 into theta. We have to convert this theta, which is given in degree, into the radians. So to do that, we have to multiply 0.5 into pi by 180. Now we will divide this value by L, that is 1.5 meter. So when we will solve this, we will have the t value that is coming out to be 4.56 into 10 to power 3 Newton meter. This is the t value that we have find. Now the only thing that we need to find here is to get the final value p. So we will put all the values here. So 2 pi n is 500 into t is 4.56 into 10 to power 3 divided by 60. So when we will solve this in the kilowatt, we will get the power value in the kilowatt 238.64 kilowatt. So this is our final answer. When we will convert this into the kilowatt, so we get the final power output or the power transmitted from the shaft will be 238.64 kilowatt. Now let's move to the next question. That is question number 2. So here is the question number 2, in which a cylindrical bar has length of 5 meter and cross-sectional area S is equal to 10 meter square. The bar is made of linear elastic material with a density of 2700 kilogram per meter cube and Young modulus E is equal to 70 gigapascal. The bar is suspended as shown in the figure and is in a state of uniaxial tension due to its self weight. The elastic strain energy stored in a bar is equal to. So we have to find out here the elastic strain energy that has been stored here. So that is given by U is equal to gamma square L cube A divided by 6E. This is the equation that we can use to find out the stored strain energy in this bar due to its self weight. So now, so we have to put this gamma will be is equal to rho into G. So rho G whole square into L cube A divided by 6E. So we have all the value. When we will put all the values here, so we will get the final answer, that is 2700 into 9.81 whole square into 5 into 10. So we have to put 5 cube here because we have to put L cube divided by 6 into E. E value is, we have given how much, 70 gigapascal. So this will be 70 into 10 to power 9. So when we will solve this, we will have the U value that is coming out to be 2.08 joule. So this is the final value of the U that we have to find out here. Now the next question, that is question number 3. So question number 3 is the moment of inertia about the bi-axis of linearly tapered section as shown in the figure in meter to power 4. We have to find out. So basically we have to find out the moment of inertia about this y-axis. So how we can find out that? To find out that, so first of all, what we will do, we will consider this half section of this trapezoidal bar. And then what we will do, we will make one what we will do, so we will try to make one rectangular section out of this, right? So we will try to make one rectangular section out of this. And from this rectangular section, first of all, we will find out the total moment of inertia of this rectangular section, and then we will subtract this triangular moment of inertia out of that to get the half portion moment of inertia. Then we will multiply this by 2 to get the moment of inertia of the complete tapered section. So what is the moment of inertia for this rectangular section? So moment of inertia of this rectangular section is given by 1 by 3 into this thickness, that is 3 into 12, that is the length, cube. So this is coming out to be 12 cube, right? Now what we will do next, we will try to find out the moment of inertia of this triangular section. So moment of inertia of this triangular section with respect to y is given by 1 by 12 into 1.5, 1.5, which is this base length multiplied by 12 cube. So when we will solve this, we will have final value of 1.5 into 10 into 12 to power 3. Okay, so actually this is coming out to be uh, 1 by 8, sorry, so 1 by 8 into 10 to power 12 to power 3. Now what we will do, we will subtract to get the final value for the half section. So this is given by 12 cube minus 12 cube by 8. Now when we will solve this, we will get 7 by 8 into 12 cube. Now finally, the total moment of inertia is given by 2 into this value, because right now we have find out the moment of inertia for the half section. Then we will find out the moment of inertia for the remaining half by multiplying 2. So when we will do this, we will have the final value that is coming out to be 3024 meter to power 4. Okay, so this is our final answer that we have to find out. Next is the question number 4 that we have to solve. So question number 4 is given by ignoring the small elastic region, the true stress sigma and true strain epsilon variation of a material beyond yielding follows the equation sigma is equal to 400 epsilon to power 0.3 megapascal. The engineering ultimate tensile strength value of this material is. So we have to find out the ultimate tensile strength value for this material in megapascal. So how we can find out that? So we have given the true stress strain relationship that is given by sigma is equal to 400 epsilon to power 0.3. So now what we will do, actually at the ultimate point, this epsilon value will be is equal to n, that is this index value. This is given by 0.3. So we will have the sigma true stress value, that is this is the true stress. So sigma t will be is equal to 400 into 0.3 to power 0.3, because at ultimate point this epsilon value is equal to its index value. So we got the sigma t that is coming out to be 278.74 megapascal. Now we have to find out the ultimate engineering strain, ultimate engineering tensile strength. To get that, we need true strain value. We will use the true strain equation. So when we will use the true strain equation, that is given by epsilon t, it is given by log of 1 plus epsilon. So we have to find out the sigma ut value, that is given by sigma t, that is true stress, divided by 1 plus epsilon. Okay, this is the engineering strain. So now we will try to find out the 1 plus epsilon value. 1 plus epsilon value, and this is given by e to power epsilon t, right? And what is the epsilon value? Epsilon t value is equal to value of n. So this will be e to power 0.3. So finally what we get 1.35. So now we will put this value here. So we will have the sigma ut is equal to 278.74 divided by 1.35, right? So this way we will have our final answer, and this is coming out to be 206.55. Now we will go for the next question. So this is our final answer for this question. This is in the megapascal. Yeah, one more thing we have to write here. This is in the megapascal. Now next we will go to the fifth number of question. So in this fifth question, what we have given, this is the objective type of question, in which a cylindrical bar P and Q have identical length and radii, but are composed of different linear elastic materials. The Young modulus and coefficient of thermal expansion of Q are twice the corresponding value of P. Okay, so for the material Q, we have given what we have given, Young modulus and coefficient of thermal expansion of Q is twice of the corresponding value of P. So if suppose alpha q will be is equal to 2 times of alpha p, along with that e q will be is equal to 2 times of e p. This is what we have given. Assume bar to be perfectly bonded at the interface and their weights to be negligible. The bar are held between rigid support as shown in the figure and the temperature is raised by delta T. Assume that the stress in each bar is homogeneous and uniaxial. Denote the magnitude of stress in P and Q by sigma 1 and sigma 2 value respectively. Which statement, which of the given statement is right, we have to find out here. So first of all, we have given these two conditions, that alpha q is equal to 2 into alpha p, along with that eq is equal to 2 into ep. So we will put these use this to find out the our relations. So first of all, we will try to find out the sigma 1. Okay, so sigma 1 will be given by p by a, right? Along with that sigma 2 value will also be given by p by a, right? So these are the two values that we find out, that sigma 1 and sigma 2 value, that is the stress that is acting here. So here what we can see, that the stress that is acting here is the same in both the cases, that is given by P by A. So that's why one of the option for this question will be this. Why this is same? Because both these have the same A value, right? So both the bars have the same area. That's why this option number D will be right. Along with that, one more option is right here, because here you see which of the statements given is are correct. So this is the multiple of correct option question. So here now we will try to find out the deflection of P. So how we will can find out the deflection of P? That we can get by, so we have to find out the deflection of the, so this is given by L alpha T P here. So now what we will get? We will get the deflection value here. So what we can see, the deflection for the Q here is more than the deflection value for the P. That is why what we can say, option number A will be right. So because as the deflection of Q is more, so that's why this var will move towards the left after heating. So right, so this will be again another option that is correct for this. Now next we will move to the question number 6. So here we have given one another question. A figure shows a thin walled open top cylindrical vessel of radius r and wall thickness L. The vessel is held along the brim and contains a constant density liquid to height h, right, from the base. Neglect atmospheric pressure, the weight of the brim and vessel, and bending stress in the vessel wall. Which one of the plot depicts qualitatively correct dependence of magnitude of axial wall stress sigma 1 and circumferential wall stress sigma 2? So you see here we have given one thin walled open top cylindrical vessel of radius r and wall thickness L. The vessel is held along the brim and contains a constant density liquid to a height h from base. Neglect the atmospheric pressure, weight of the vessel, bending stress in the vessel wall. Which one of the plot depicts qualitatively correct dependence of the magnitude of wall stress sigma 1? So we have to find out the sigma 1 and uh, sigma 2 value, right, on y. Basically how this value depends upon the y, that is what we have. So if we try to get the axial wall stress, that is the given by the sigma 1, so this value will remains constant. Why this value will remain? Because this value will depend upon the total weight of the fluid and the total amount of the fluid, right, and which remains to be constant. That's why sigma 1 value will be constant. So what we can see, sigma 1 value is constant in option number A only. So that's why we can say option number A is right. Along with that, we can also calculate the sigma 2 here. So if we calculate the sigma 2, so we will get sigma 2 will be is equal to TD by 2T. So this will be given by rho G H, so rho G H D by 2T, right? Now, so here what we can see that sigma 2 is directly proportional. So that's why this option number A will be. Now let's move to the last question for today. This is the question number 7. So a beam of length L is loaded in XY plane by uniformly distributed load and by a concentrated tip load parallel to the axis Z axis as shown in the figure. The resulting bending moment distribution about the Y and Z axis are denoted by My and Mz respectively. Which one of the option given depict quantitatively correct variation of My and Mz along? So this is very easy question. Actually, while looking at the figure only, we can solve this question. So first of all, one UDL is there. So that as this UDL is acting towards the downward direction, that's why this will produce the negative bending moment along the z-axis. That's why, and this will be in the parabolic. So this can be the right option. Along with that, which other can be the right option? So here we can see uh, only option B we can see that that could be right one. Along with that, you see this point load which is acting horizontally, this will produce the linearly variation bending moment and that will also be positive. So that's why option number B will be right here. So this question is very easy by looking at the figure we can solve. So okay, this is it for today. Remaining questions we will solve in the next video. So thanks for watching. Goodbye.